Hi, welcome back to our second video for 3.2 exponential decay connecting to negative exponents. In this video, we're going to look at applications of exponential decay, starting with my favorite, nuclear radioactivity, also known as half-life problems. So Ontario gets lots of its energy from nuclear power plants, and what they do is they'll take certain elements and they take their atoms and they break them apart or split them in half. And what happens is it gives off tremendous amounts of energy. And when this happens, one of the byproducts is that we get isotopes of that element that are radioactive, and we call it radioactive waste. So it's important for physicists, engineers, anyone who's working in those nuclear power plants to properly handle that material. And one of the things they need to know is how long it's going to be radioactive for. So the half-life basically tells them how long it takes for half of it to decay, meaning half of it to not be radioactive anymore. So some of the other examples we're going to look at, not in this video, but they'll show up in homework and in other lessons. We're going to have depreciation, which has to do with any assets or items that lose value over time. So like a vehicle or an electronic, maybe a laptop or something. And one of the other ones is the concentration of medicine in the bloodstream. So if you're going into nursing or medicine, you'll appreciate these examples. Basically, it's important for nurses and doctors to know how much medication to give a patient. So they need to know how long that medication is going to stay present in the bloodstream. So these kind of questions are important for them. All right, let's get into our first example. So we have uranium-239. So this is going to be an exponential decay or a half-life question. So it says when uranium-239 decays, it forms a different material called plutonium-239, Pu-239. Apparently it smells pretty bad. It's a highly toxic waste material, and it has a much longer half-life of 24 years. So um, other materials that they use for nuclear power, their half-life isn't as long as plutonium. So plutonium, the half-life is 24 years. That means it takes 24 years for it to lose half of its amount. Um, Other substances, they'll only be radioactive for a couple years, so they'll have a half-life of a couple years. So plutonium is quite longer. Anyway, they want us to determine approximately how long it'll take for a 50 milligram sample of Pu-239 to decay to 10% of its original amount. So we're starting with 50, and in 24 years, we'll only have 25. And then another 24 years, we'll have half of that. We want to know how long will it take so that only 10% is remaining. Well, we probably should first figure out how much 10% is. So we can multiply 10% times 50, or 0.1 times 50 to get 5. And then we could try to see how long it'll take for only 5 to be remaining. So I've set up an Excel spreadsheet in order to do this. It's a quick way to kind of find an answer that we're looking for. So this is already filled out. As you can see, I have under column A, we have the half-life periods. Column B, we have the time in years. And under column C, we have the amount remaining. So notice after 0 years, there's 50 milligrams remaining. It's not till 24 years that we have our first half-life, and only 25 milligrams will be remaining. You can also see, if you look up a little bit to the left, where it says Fx, and there's an equation, it says equals C2 divided by 2, so kind of right above where it says column A here. So it says C2 divided by 2. That's an equation that gets applied to all the cells in order to calculate the next cell. So all I did was enter in 50, and then I used that equation to calculate everything else. So we're trying to figure out how long will it take for there to be only 5 remaining. So that 5 is somewhere between 3 and 4 half-life periods, or 72 and 96 years. Okay, so Just to kind of show you a little bit how this works, that equation, if I hit that I have stored, when I use the fill button, I can drag out and keep applying that equation. So you notice it's a really quick way to generate a lot of values. And you can always see that we're multiplying by a half to get the next value. Okay, let's go back to the PowerPoint. So I've imported that table here, highlighting the important information. So if just using the table, we're not going to really get a quite accurate result. We just know it's going to be anywhere from 72 and 96 years. So to get a little bit more accurate answer, we should probably develop an equation. So notice the way how the equation works. We take the starting amount 50 and we keep multiplying by a half. So depending on how many half-life periods. So an equation, we could take this half and we could just raise it to the exponent n, where n could be the number of half-life periods. So if we wanted to know, like after 3 half-life periods, we could put 3 in for n, and we could calculate that amount. Okay, I'm just going to erase this and this. Okay, and we'll talk a little bit more about that equation. So okay, there we go. All right, so alternatively, we could apply a systematic approach to solving this by using the equation an equals 50 times a half raised to the exponent n. So that equation that's in green there, we could use that to calculate the amount remaining. So where an is the amount of Pu-239 remaining in milligrams, and n is the number of 24-year half-life periods. So if we wanted to know after 1 half-life, we could put 1 in for n, and we'd have 50 times a half, and we get 25. So hopefully you can see how this equation would work. So how does this help us? Well, if we're trying to figure out how long it takes to just have 5, we could actually substitute 5 into the equation. Okay, so we could substitute 5 in for a, and we would have that equation there. And now we can try to simplify this in order for us to get a value for n. So we can divide both sides by 50. So divide this side by 50, divide that side by 50. So 5 over 50 equals a half to the exponent n. Notice we've never ever algebraically solved for an exponent. I will show you guys how to do it a little bit later. For now, we're just going to use a systematic or kind of like a trial and error approach. So right now we have 5 over 50 is 0.1. So we have 0.1 equals a half raised to the exponent n. Well, what does n need to be to satisfy that equation? So by trial and error, I got 3.3. I can actually get a number a little bit better than that too, but just to show you, 1 over 2, and if I take this and I raise it to the exponent, let's say 2, I get 0.25. So I'm trying to get something that's 0.1, right? I'm trying to figure out what does n need to be so that I get 0.1. So if I make this higher, like 4, I get 0.06. Well, that's too big because 0.06 is too small. I just want 0.1. So if I put in 3, notice I'm pretty close to 0.1. I got 0.125. I could try adding a couple decimals to this, like 3.2, and that's a little bit better. Could try to go a little bit bigger, 3.3, and that's pretty close. 3.3, I get 0.101. That's almost exactly 0.1. So we can go ahead with that there. So if n is equal to 3.3, then that means 3.3 half-life periods. If I multiply that by 24, I get the total number of years. So therefore, it'll take about 79.2 years for the PU. This should be 39 Pu-239 to decay to 10% of its initial amount. Okay. All right, that's it for now. In the next video, we'll talk about our exponent rules. I'll see you in the next video shortly.